So, good morning, everyone. I am going to talk about as a precursor to tomorrow's talk, where my colleague from Poland, Mirek, will talk about the Xeon plus FPGA family that will be introduced soon. Today, I'm going to just spend some time with you on basically explaining how FPGA is getting used since the beginning of the FPGA story on scientific workloads, and how what sort of tools we have today to help high-level algorithm designers to benefit from the technology. Just out of curiosity, I want to understand how many of you are familiar with what FPGA is. Can you just raise your hands? So you all are familiar with the FPGA, so that's good. I will skip some of the introductory slides about the inside of the architecture now. So what I'm going to talk about is trends that we see in my region, which is basically EMEA region. I look after high-performance computing accounts, which includes oil and gas, scientific workloads, government workloads, finance, medical, healthcare, all those sort of things. And I'm also involved in engagement with CERN, various groups within CERN we are talking, and also Square Kilometer Array project, which is, I'm sure you must have heard, it's the astronomical project for getting implemented in Africa and Australia. So the science workload and also some of the commercial workloads, they show interest in FPGA for various reasons, and I'm going to explain the trends a little bit. And then I was going to go through a little bit of a background on FPGA architecture. I will skip that quite quickly. I'll talk about various forms of parallelism that FPGA can help explore for your custom workloads. And then I'm going to talk about briefly the tool flows we have for designing FPGA-based implementations. So just I'm supposed to show this is a typical disclaimers that the information here doesn't grant any license or cannot be shared without consent, etc. So that will be part of the slide set. I am going to briefly give you my personal overview of what's going on in the accounts that I talk to. There is always a demand for increase in the core performance of the next generation system, and this is basically motivated by two reasons. One, there is more data coming from the sensors or from the end users, and the second thing is the algorithms that are getting run are getting more complicated, they are getting more advanced. AI, for example, deep learning, in comparison to statistical workloads that were doing the job of the AI in the past, AI is giving better accuracy after getting after finishing a good session of training, but in the expense of a huge increase in the computation workload. So it definitely is the way forward for many of the areas that we see in the high-performance computing segment, especially recognition, identification, tracking type of things, and also giving meaning to scenes and the text. But on the other hand, the things that are getting done with the deep learning or to enable deep learning, the computations are really comparably a lot. And the second thing is a trend we see is the power consumption budget is trying to be either kept constant while the demand for compute power is increasing, or the power is also getting cut down by various requirements for the next generation systems, either because of being more environment friendly or because of the mobility of the system. Power needs to be managed properly, and these basically two contradicting trends of increased compute power and the lower power requirement or power consumption requirements. They push people to analyze what can change in the existing way of doing things for the high performance systems. If you try to scale up CPUs or the data centers with more nodes, it increases the power as a result of that linearly. if you try to do things with architectures that are running faster, that increases also the power linearly. If you try to parallelize systems, it has an advantage to, and I'll show you one slide about why parallelization helps. But the system that we typically see on the parallel programmer's agenda, which is the GPU, it seems to offer the solution of parallelism in a quite a high power budget. So that's where the way FPGA tackles the parallelism problem may help solve some of the issues, and that's where we actually see the trend of exploring FPGA more and more. Intel has, before they bought Altera, there was a sort of public announcement about projecting at least 1/3 of the cloud nodes by 2020 to have FPGAs on them as a custom acceleration sort of medium for being able to tackle things that are not necessarily changing every second or every minute. By the nature of the FPGA, once you have an efficient solution there, if you can manage to keep it there long enough, the overall power advantage, it surpasses the time you consume to develop that solution for the FPGA. And we've seen in the past years public announcements from Microsoft and from other big cloud vendors that they are investing on FPGA-based solutions on their cloud platforms. Bing has been sort of the most popular public announcement in the last 2 years to benefit from FPGA acceleration. They said that it was basically twice the performance of the CPU-based acceleration brought by the FPGA-based implementation. On the other side, they also said, Microsoft also announced that they actually have in every node in Azure, they have an FPGA card. That was one of the biggest announcements we have heard. On the other side, there are others like Baidu and other vendors who are investing on FPGA-based acceleration for different types of workloads, such as machine deep learning and also other workloads that they see fit. In my region, for example, there was a public announcement from a DNA sequencing company who said that they chose FPGA because the performance that they achieve versus the power is the best fit for their mobile platform. All those things contribute to the validity of the claim that we will see a lot of FPGA nodes on the cloud later on, in the coming years. How does FPGA becomes useful in a high-performance system? There are 3 ways that we envisage FPGA to be useful. The first way, which is on the left-hand side here, that's the typical acceleration offload medium, such as the GPU or other acceleration platforms. So what you see here is the standard use case of CUDA or OpenCL being able to accelerate CPU workloads by using standardized interfaces such as PCI. On the other use case, on the right-hand side here, you see FPGA sitting in the middle to the storage medium. And in this case, FPGA could actually offload the CPU's job of trying to decompress or compress the data going in or coming out of the storage, and also do the encryption, decryption on behalf of the main system controller. And that way, it can actually accelerate and reduce the cost of the power and reduce the power consumption of the data center significantly. The one on the bottom is the more like an embedded use case, but we see that being more close to a data center style environment with the announcement of the MCP device, which will be discussed tomorrow. So what we have here is, if you have different types of sensors trying to bring data in, this can be either one-dimensional signals such as radar, or such as A to D channels bringing data from various mediums. In CERN, it can be an accelerator or an experiment producing sort of proton crash data, and you capture that, and then you digitize it, and then you bring it into your cloud platform to understand what went on during the experiment. In the case of some of the visual workloads, video captures could bring into the data cloud from various sensors, not just one. I mean, just the previous talk from Holographica, we heard that there were 48 videos that were brought in. So in those sort of scenarios, could actually benefit from FPGA capturing multiple channels and then doing the first level of pre-processing before the data reaches the CPU for further in-depth analysis. And in the case of data reduction, FPGA is a good medium because most of the data reduction techniques are very control-wise, they don't have too much control. You have a very fixed job of trying to do some arithmetic function based on certain criteria, and then the data suddenly becomes more relevant, and then you basically reduce the cost of the overall system by sending only the most relevant part into the CPU system. So these are the three cases that we see in the engagements we have with different customers, different market segments. Today, my talk will be mostly about trying to understand how the parallelization can actually happen within FPGA. There are some similarities to GPUs, but there are also some differences to the GPU, so I would just like to describe those. Before going into the parallelism discussion, just a quick overview of FPGA. What is FPGA and what is inside? What does the inside look like? So it's a blank canvas with very tiny little building blocks that fill the whole chip. And in between those tiny little blocks, we have routing wires. So basically, if you look into a portion in a zoomed-in fashion, you have basic element with a lookup table and some very tiny arithmetic based on 1 or 2-bit logic. And then those things come together and then make groups of soft logic. That's what they call soft logic. And then in between those soft logics, there are wires in everywhere that basically are getting programmed by the binary file that's produced for your own design. The compiler decides to make a certain type of connection between different parts of the logic to give the impression of what you are trying to do. The other building block is a memory block. Any building blocks that you see are in column-wise fashion in the Intel FPGA. So there's a column of memory blocks, and there are multiple columns of memory blocks, and each of which are 20 kilobit sort of capacity. You can use this 20 kilobit size individually, or you could group them and then make deeper or wider caches for various storage requirements. And the other thing that we have is DSP blocks, and you have again columns of DSP blocks in the chip, where each of which has some multiply and some add functions. In the latest generation of the devices that we have out in production, which are called Array 10 FPGA family, we have support for 18-bit precision multiplications, 27-bit precision multiplications, and single precision floating point multiplications. And in a single DSP block, you either have two 18-bit precision multipliers, or one 27-bit precision multiplier, or one single precision multiply and single precision add. So that's the typical building blocks of the core FPGA. And based on your compiler's decision on how to connect the building blocks to make up your own design, you see different types of routings being used. Sometimes there are sneak paths between the components that can be utilized to give you higher performance. Sometimes you need to use the soft logic routing resources that are basically going from one hop to the next, and then that defines how quick your FPGA can run. And today, the fastest speed you can expect from Array 10 FPGA is around 490 megahertz that I've seen, like a full chip running for a communication system. In the next generation, Stratix 10 we expect to see beyond 800 megahertz for the system clock. And the numbers that are associated with the building blocks that I've shown you, I just wanted to highlight a few of those here. This is the largest Area 10 FPGA family member, and in the largest family, we have 1500 DSP blocks. That means we have single precision multiplies and adds in parallel. There are 1500 of them that can run up to 400, 500 megahertz clock speed. In most cases, system clocks by the customers are kept around 300 or 400 megahertz, or maybe even less. But if you think about the parallelism of those resources times the frequency, you can see how many teraflops you can get from one chip. And in this case, Area 10 is expected to be giving you around 1.5 teraflop, and the power consumption for that 1.5 teraflop is in the range of 40 watts. So that's where the power of the FPGA is seen. I mean, you have quite high performance, but in comparison to the similar performance from a GPU-based implementation, the power budget here is quite significantly less. So, I'm going to talk about parallelism a little bit. On the left-hand side, you see a snapshot from a Xeon processor, a multi-core Xeon processor. And in the middle, we see a similar snapshot of the Xeon 5 that our first speakers have shown us. And on the right-hand side, there is the FPGA die image. So from left to right, we see different levels of parallelism being explored on the chip level, coarse grain to fine grain. When you look when you look to the chip level parallelism that's being put into the architecture, actually you think that, okay, I have coarse grain parallelism being explored by my algorithm on the left-hand side, and on the right-hand side, I expect fine grain parallelism to be available on this architecture. If you were able to use individual bits by themselves, that would have been right. But in most cases, individual blocks by themselves are not meaningful to you. The compiler tries to combine them in a meaningful way to make up components, virtual components or soft components, let's say, to give you what you need. Sometimes it can be an arithmetic function such as cubic or exponent or logarithm type of thing. Sometimes it can be slightly bigger, more complicated blocks that are maybe edge detector or corner detection in the visual context. It can be an interpolation or an FFT. And in those cases, you see the meaning of fine-grained parallelism actually become irrelevant, because you see just a blank canvas where things can coexist in parallel because of the fine-grained parallelism, but on the actual fabric that you are seeing in the application layer is not fine-grained anymore. So that's what I wanted to explore in the rest of the slide set, to show you how we explore this blank canvas and the coexistence of multiple functional blocks and give you different types of parallelism. And before going into that discussion, I wanted to also just touch on what problems we are solving. And we talked about the problem of power briefly. We are trying to solve the power problem by exploring parallelism. We are also trying to solve the memory load problem, not because of the parallelism, but because of the way we can use FPGA, and I'm going to touch that in a second. And the main discussion will be the middle one, which is the types of parallelisms that we will be seeing. So if you think about how the different generations of semiconductor devices have increased the capacity of the core performance in relation to Moore's law, you see a curve which basically was almost realized by multiple vendors independently throughout decades. And on the bottom graph here, you see the curve where the memory technology improved its capacity and performance. And there's a big gap, and the gap has increased over years. And that basically pushed people into ways to try to rethink how they can use the next generation node in a way which is not same in the previous generation node. And this basically is one of the key things that's pushing most of the scientific workloads today. I mean, you have many issues regarding to memory-bound algorithms or memory-bound applications, and in most cases, availability of the data is the biggest issue for getting performance from an existing data center or an existing high-performance computing cluster. The typical average usage of the processing capability of a data center is on average around 3%. This is statistics by, I mean, it was a public statistics, I don't remember the actual link to it, but the 3% capacity use is purely because the data is not readily available to the nodes as soon as you need them. And if you extrapolate what that means to your problems, you will realize very quickly that if you try to maintain how you approach the problem as you have approached in the recent years, or in the let's say in the past years, with CPU-based codes such as fortran codes or single-threaded codes, then you are bound to be suboptimal on what you provide as a service to your colleagues or to the scientists. So there are ways to get rid of this if you were to able to provide technology which can actually help access data which is closely aligned with the processing nodes. High bandwidth memory, HBM, spelling mistake there, I think high bandwidth HBM is a way to solve it, and multiple vendors are working with that. But on top of the high bandwidth memory approach, where the large bandwidth is available inside the chip, you actually have another way to benefit from the data that you already brought into the chip. And if you keep it inside the chip longer without pushing back to a large chunk of memory for the next kernel or next task to begin, you actually save a lot from the memory bandwidth, and then you can achieve more, and you can explore the compute capability quicker. So I'll touch on to that in a second in the later slides, but before going to that, into the depths of that, let me explain how the power law actually manifests itself in a system. So if you think about the power consumption, dynamic power consumption formula that most of you may be aware, there is capacitance of the nodes, there is the voltage that you apply, and there is the clock frequency. And then there is an unshown factor, which is the toggle rate factor for the dynamic power consumption of the node. That gives you the dynamic power. Static power is device dependent. There is not much you can do because it basically is defined by the voltages that you apply onto this VCC and onto the threshold on the VT page. And that's somehow defined for you. And the leakage is also relevant to the different technology nodes. But this is the one that you can play with based on being able to control the toggle rate of the algorithmic implementation and also the overall capacitance. So toggle rate is related to frequency, but it's also related to the algorithm. Frequency itself is the clock frequency you run your chip with, and also, but the capacitance is something that relates to the amount of loads that a source sees to drive. And in the case of a parallel implementation, which is shown on the bottom, the capacitance that is observed by a driver has been multiplied. If you wanted to do the same job in this parallel system around the same time frame, instead of running the whole job with the clock frequency of f, you could actually run individual parallel jobs with a f over n, where n is the amount of parallelism you explored in here. So you basically have a different formula to represent the overall power, dynamic power that comes out of the system. And if you think about different numbers associated with the parallelism you explored and the amount of capacitance per parallel node and how it impacts your overall function, you could actually get the same job done in a parallel system in a less power-hungry way compared to a single node implementation. So parallelism helps, but of course, to make it help, you need to think about other things on top of it, which is the one that I mentioned here. Think about the toggle rate. Toggle rate is the biggest killer for the dynamic power, so I'm going to touch onto that and how it relates to FPGA implementation. Another implication that we have seen over the years is how the roadmap to the exascale has been visioned in respect to the core technology or core strength of the transistor capability versus how much parallelism is required to reach that. So if you look into the jump that you have needed from giga sort of scale to tera scale, during those years, some of the performance boost came from increasing the capability of the transistor, and some of it came from increasing the parallelism. If you wanted to see what's happening on the exascale from petascale, see what happens to the transistor capability increase and how much parallelism is needed in the system. So without getting into the memorable or powerful problem, just think about what is required to get your overall performance for your data cluster, high performance cluster, to an exascale manner. You cannot expect that to come from the technology node. It will come from parallelism. So it's an unavoidable problem. So it applies to both the case of the GPU and on the FPGA. But this is a clue which I think relates quite dearly to our discussion over the 2 days. So compute wall, the parallelism wall basically is being explored by different types of parallelism, which basically show itself as vectorization and data parallelism and also task parallelism. So there were architectures implemented by the CPU vendors or by the GPU vendors to explore both. And they both have a meaningful approach to solve this parallelism problem. They have relevant areas where data parallelism helps, but there are also applications where data parallelism actually not helping as much because you can't extract the data parallelism out of the algorithm that you are doing. I mean, in those cases, task parallelism is the way to go. So how can we see task parallelism and data parallelism in a typical code base? If you think about these multiple tasks that are independent from each other, and if you try to if you want to co-implement them in a device or in a medium and run them at the same time, that could actually give you an overall time reduction for the whole task. But if you think about any of those tasks being explored further with data parallelism, you could actually try to vectorize or try to run multiple instances of the same task to be able to give you data parallelism within the tasks itself. So if you think about how GPU today would help with both those cases, or how CPU is geared to do those, or how Xeon Phi is geared to do those, think about all those things and the restrictions coming from the architecture, and then think about how FPGA could actually help by the picture that I'm going to show you in a second. So I was just warned about the time, so I'm going to make it a bit quicker. So this is an instruction. I mean, for most of you, what I'm going to explain is going to be very simple to understand, so I'm just going to quickly rush through. An instruction to basically make a multiplication with a constant and then add it to a memory location. So if you were trying to do it on a CPU style implementation with sort of assembler commands, this is what you will be doing in a couple of timestamps. You will be running it on an engine which is geared to do this sort of time multiplexed instructions on a cycle by cycle basis, and then give you the overall result after a certain amount of clock cycles. If you think about what you use every cycle and what you don't use every cycle, in most cases, some of the stuff which is being powered there stays idle. Not everything is utilized. So you basically power the silicon, but you don't use it. And actually, when you use it, there's a big change from one cycle to the next on the individual nodes. So you basically make a toggle which contributes to the dynamic power. And you change basically how you use that ALU or the typical one-level architecture that I've shown in the previous slide on different cycles for the 6 assembly commands that I've shown you. And you basically implement the instruction that was able to, that was supposed to multiply a number getting loaded from the memory with 42 and add it to something to the previous value of another index from the memory and then store it back to the same index. So that's how it would have happened on the CPU. And in the FPGA, you could actually just visualize this as a starting point and actually finish with this in the FPGA as well. So in FPGA, you could have registers storing your values in the way that we have described here. You will have a physical multiplier that will be able to multiply the content of those two registers and physically pass that into a separate adder that will be able to add that another register, bringing the data here and then do the storage on another register. So you have as many registers as you like, you have as many arithmetic operators as you like, and they are connected in a way which only makes sense for your expression and nothing else. So the connections, the amount of logic that's being implemented by the compiler, and the amount of registers required and used, they are all defined by your code. So you have full control of what you put into the chip in terms of powered portion of the logic. And then you see that instead of trying to work on a time multiplex fashion, you basically have explored special parallelism. That's basically sort of special availability of those instances in time. And this is the starting point for being able to understand the next parallelism that I'm going to describe. So this is what happens on FPGA. And if you think about how you would have parallelized that on the FPGA, there are a couple of ways to think about. First of all, you will have multiple instances of those in the FPGA because you have thousands of those resources. But if you do that, you actually waste your FPGA resources to achieve a performance that can come from actually one instance. So if you think about what's going on here, you have workloads or work items in the context of OpenCL being scheduled on 3 different physical instances, and then they start, and then in a couple of cycles, in 1 and 2 cycles, they finish the job. So these are basically the inputs, and these are the outputs for the parallel threads. So actually, the parallel threads that you see here, 3, 4, and 5, are scheduled on top of the existing ones, which is 3 after T0, T1, and T2 are finished. Is this the best we can do? No, we could do it probably better. If you think about your workloads in being available in a time series fashion, you could only think about one instance to start with, and then think what will happen in terms of loading different work items into this, and then see whether parallelism is required further than one instance of physical instance of this. So in the first cycle, you see T0 being loaded into the registers. In the second cycle, you see the operations taking place, and T0 now reaches the storage unit, and then at the same cycle, T1 comes to the input register stage, and T2 is basically getting loaded. And on the next cycle, T0 is completely finished, T1 is on the output stage, and T2 is on the input stage, and then you continue like that. So at any given point in time, you see that this physical implementation is able to house 2 work items at the same time. And this is because of the pipelining registers. So what we see here is what we call pipeline parallelism. This was a very simple example. Think about the actual code bases that you have and how much pipelining depth you would have. If you have hundreds of pipelining registers, it means you could actually have parallelism from a single physical implementation in the ranges of 100. So 100 work items could coexist in a one physical implementation of the algorithm at any given time. Just basically assuming that you have enough work items to fill the pipeline. Sometimes the pipelines are thousands cycle deep, sometimes they are hundreds cycle deep. It depends on what you are trying to solve. So we basically now thought about pipeline parallelism and physical parallelism in both examples here. So in the pipeline parallelism case, in comparison to the previous diagram that I've shown you, you basically start the new work item almost every other cycle, or every next cycle. So you have explored the one physical instance with the parallelism that can be shown in this sort of diagram where there's an overlap between the processing time. I am rushing through, so please excuse me about not giving too much more explanation on those. So how does this get explored by the high-level tools? High-level tools are such that basically we try to abstract away the difficulties of programming FPGA with RTL languages. So we try to make it as user-friendly as possible to the software designers and try to make it accessible from C-style languages. Saying that, we basically have C compilers, we have OpenCL compiler, and we have Simulink compiler to explore these types of parallelism that I tried to describe in my previous slides. And when you think about which software tool or high-level tool fits which type of user, we have a variety of options. For algorithm designers, we see Simulink, MATLAB being sort of relevant in several institutions. We have OpenCL being relevant in several institutions. For software designers, which are basically targeting just FPGA as a platform, OpenCL is the best way forward. But people who are in the embedded space, who basically are trying to do more hands-on with the ingesting of the data into the FPGA, doing something more real-time with it, we see our C++ compiler being handy to generate the components in a more optimal fashion and being integrated in an OpenCL framework maybe. And then everything that you see on the left-hand side here, those three, they can be turned into designs that can utilize our backend compilers to give you the FPGA binary. These are all basically behind the scenes. The one that you see here is behind the scenes. The ones that you interact with are the top ones that I show there. So OpenCL is the one that I was going to talk about, but before we're running out of time too much, I wanted to just quickly show you a few slides on the compiler technology. So we have three different front-end compilers for three different tool sets we have today. In future we will have more. Basically, front-end tools are able to parse the language and then give you very quick feedback about whether the language is functionally appropriate, and you can emulate in this very quick turnaround time. On top of emulation, we produce reports for showing you how much FPGA resources will be used in terms of an estimate, and also whether you will have for loops being unrolled and then run iteratively quite quickly, so iteration, internal, etc. They are all reported by the front-end tools in a matter of seconds. So that iteration can actually be very productive for being able to target FPGA from your today's workloads. And on top of, after you have a good sort of understanding of the functional verification, you basically continue with the stages, which is shown on the bottom. There is a different compiler flag, which basically you add or you actually remove to take it through the full compile. And when you do the full compile, it becomes ready for FPGA implementation with all the optimizations that are done by the backend compiler to give you a target Fmax of your choice. And then you basically download it into the FPGA and then you run it. How do you download? How do you run? OpenCL take care of all of those. So if you think about how OpenCL has envisaged the model of use case for different compute devices and a host device, the heterogeneous platform model, which was explored by GPUs and also FPGAs in a similar way, has the concept of processing element, compute unit, compute device that basically gives you the details of your accelerator node. And they all talk to a global memory, which is also basically accessible by the host. And all the exchanges that you see, standard exchanges that you see, happens through the global memory. So if you think about how FPGA and GPU explores that, the access style is similar. The both of the cards will work in a very similar fashion in terms of getting data passed from the host into the global buffer and then being accessed by the kernels. In the case of GPU, you see a homogeneous architecture of processing elements and then compute nodes and compute device, and then there are some specialized structures here. On the FPGA, there is a fine-grained structure which has nothing to start with, but when the compiler finishes its job, it's being turned into a custom implementation which only has things that relate to your kernel, and that's the good thing. So you only have kernels that are as deep as required by your code, and you have as many instances as you like to have by using pragmas or attributes or vectorization. And then you have different kernels occupying different size of FPGA resources based on the complexity of the kernel. And the other good thing is that instead of going back to the global memory every cycle, you could actually pass data from one kernel to the next, and then from there to the next, and then from there to the next, and then leave from FPGA after finishing all the complex steps that you wanted to accelerate on the FPGA. This is our great savior, which is called channels, kernel channels. And if you use that, you basically maintain the data onto the FPGA, on the FPGA longer, which helps to remove your memory load problem. That's the one which I wanted to relate back to the whole discussion. So, OpenCL use model is pretty known by most of you. Maybe it's something that you may not have initially recognized is the need for the offline compiler for the kernel. So, because FPGA requires the kernel to be compiled previously before the host code is run, so we have an offline compiler that takes your kernel code, prepares the binary, and then from your host code, when the run is actually initiated, create program from binary and build program from binary, basically receives the AOCX file's location and the name, and then it programs into the FPGA during the run of the host code, and then you execute your kernel, and then if you wanted to change to a different kernel, you could do so by pointing to a different binary image. But all your different kernel images needs to be pre-compiled and ready for the host code to be used. And this is the typical steps that we go through for finishing an OpenCL based implementation. That's the first level compile that gives you emulation and the report optimization report files. And then if you, this is the emulation line. That's the first stage compile for reports, which gives you very valuable information for optimizing your code. And then once you are happy with this sort of feedback, you go and make the full compile and add this -- profile parameter to the compile line, which actually adds counters into the global memory accesses, and that basically takes back available information from runtime to show you how much memory bandwidth was utilized by which kernel, so that you can optimize it further. And to make it more productive, we are investing on bringing library components on various fields of science. Genomics has been one of the focus areas. We are preparing components to accelerate compression and encryption as a software function, so software callable functions of FPGA. For networking, we have network access directly into the kernels to accelerate and basically make it low latency to process data coming from Ethernet. For data analytics and actually deep learning, we have a stack of software and hardware that is accessible by the high-level frameworks such as Caffe, and in the future it will be TensorFlow in the very near future. And basically, based on those, you could benefit from the FPGA fabric to give you acceleration of the deep learning tasks or other tasks that we see here. So none of these requires you to become hardware experts. You could try to maintain your skill set as of today and just try to make use of the available libraries when they, by including them to your code. There is only a bit of a new learning that needs to happen for being able to get the best performance out of the FPGA with your custom codes that are not library based. You need to understand how FPGA architecture is and the way to extract performance from it. Scholes is a typical example that finance customers have shown interest in the past, and then here, for example, with an FPGA and 4 data DDR memory, we were able to show quite a bit of a processing power and surpass the other devices quite easily with only one chip. And to show that actually what we were doing is using a very little amount of logic in the FPGA to get that. Machine learning framework is available today, and we have a dedicated product for it. If you are interested to try it, it's called Vista, Deep Learning Inference Accelerator, that's the product name. And it basically can accelerate AlexNet, GoogleNet, and some other topologies on the FPGA. And that brings me to the end of the discussion before leaving you with the copy address. This is the configuration.
Thank you very much, Suleyman. Since the topic break is over, so we can ask questions. So please, some questions.
You mentioned that there are a lot of multiplier. I understood you correctly. Is it expected in the future there will be other type of rebate logic, like divider or so?
Such as what?
Such as divider or any other kind of rebate mini logic?
So in terms of hardened arithmetic, I don't see multiplier and adder being added by other things, because those dividers and other stuff, they have so many different parameterizations. If you put a hardened divider, you make somebody happy, but some others will be quite unhappy to say, why didn't you put an extra bit of precision so that I have better dividers? So for the things that needs a lot of parameterization and a lot of customization, we tend to keep that option as a soft IP rather than a hard IP.
So a multiplier was basically a sweet spot.
Yes, exactly.
Okay, and one more question, sorry. You mentioned that a small example when you add multiply with 42 and then add memory, and you said that in normal CPU the utilization would be not that great, but out of order running and high testing are there to hide those problems. Do you believe those are not enough to solve this problem? I mean, to be utilized fully at least on core?
So there are a couple of different aspects to that question. One of them is whether I believe that's the best approach. It depends, because you are running the CPU faster, and you are faster than FPGA, like in the range of gigahertz, versus like we are running around 100 megahertz, hundreds of megahertz, let's say. So what you are trying to do is you are utilizing this small tiny ASIC by changing its configuration every clock cycle to make a different behavior come out of it. You are paying the price for changing its configuration, changing the way the capacitances are loaded, so you are paying the price of power. Whereas in FPGA, the clock frequency is lower, and then you have dedicated things that are connected to each other with some wiring that only makes sense for your logic, for the operation that you are trying to do. When you needed to do a different operation, you don't try to map that new operation into your existing logic. You wipe it off, you start from a new set of code, and the compiler compiles a new optimized version for your code. So for every new application, we have a new blank starting point, whereas for the CPU, everything is getting mapped onto some ASIC which is being predefined by the CPU designers. And I don't say they are doing a bad job, they are doing a great job, and they have multiple pipelining strategies there, which basically is exploring, as you say, look-ahead instructions and also fetching and making it ready. But the price that you pay is power there, and power is a big issue going forward.
Thanks.
Thank you. One more question.
Thanks. So I wonder what full compile cycle times are, because there are systems which you can't effectively simulate, such as real-time data processing systems. And I have only used Silex's tools, but the compile times are outrageous, like 20 minutes for simple design. Are Intel working on improving full compile time cycles?
So yeah, we are working on improving compile time. We are, in the bigger devices, we are beyond 40 minutes, so it can take a couple of hours for largest array time, for example. But our target by the end of the year is to reduce it significantly so that it becomes less of an issue.
Thank you.